Alright, in this video we're going to discuss tolerances as a concept. We're not even going to get into true GD&T here in this session. Certainly in the next one we'll start dipping our toe into it, but what I want to do is review dimensions and tolerances and make sure that we're clear on the distinction between the two and how conventional dimensioning and tolerancing is handled and the problems that it causes. I try to make a distinction between geometric dimensioning and conventional dimensioning and tolerancing, and I'll often use the term Cartesian dimensioning. Now that's sort of a fancy word, but it sort of describes the XYZ coordinate system that we're all pretty much familiar with if you've worked in the machine shop. Most of your machines and the axes on the machines work on a Cartesian system where we have three mutually perpendicular axes and we move along those axes. I want you to have that mental picture in mind here because it's going to become essential to understanding geometry and the tolerancing that goes along with it. And it's also going to become important when we talk about constraints and datums and that sort of thing. So anyway, this is going to be focused right now on just old school Cartesian dimensioning and tolerancing. We'll review how those tolerances are expressed and how that system of Cartesian tolerancing produces an unwelcome effect and sort of limits our control in how we can define the tolerance zone of a feature. Now you're going to hear that term tolerance zone a lot. I want you to write it down because GD&T is all about the tolerance zone. When you see what limited control you have with Cartesian dimensioning of the tolerance zone, you'll realize that how powerful a tool GD&T is to give us complete control of that tolerance zone. It will allow us to define its size, its shape, its position, and believe it or not, we'll actually be able to adjust the tolerance zone on the fly. This is a powerful feature of GD&T and probably the thing that saves the most money over the course of manufacturing is the ability to, one, understand and adjust the tolerance zone as need be. And I'll give you a good example later of how you sort of do it anyway when you're making things fit at home. The GD&T is going to do that formally where you would do it informally. Okay, so let's step off into conventional dimensioning and tolerancing. I'm going to move away from the camera a little bit. I won't be in the frame too much. I'm trying to stay focused on the screen so that you can see what I write. After I view this video, I may have to change my approach here a little bit, but I am trying to stay on a tight focus. If it seems like I'm shouting, I probably am. I'm trying to make sure that the camera picks up the sound adequately. Obviously, I'm going to have to get a better and more professional setup here for sound, since the only thing that's picking up the sound right now is the camera itself. So if I sound a little distant or a little echoey, it's because I've stepped away from the camera. But anyway, let's take a look at and harken back to our blueprint reading days. If you had me for blueprint reading, we certainly discussed this a fair amount, and I want you to understand this completely so that you have a good grasp of tolerancing in general, because that is a day-to-day thing in the technical trades. Okay, so where do we start out? We start out with the concept of a dimension. And the tolerance. Okay, the first thing to remember, and it's easy to forget, is that the dimension and the tolerance are two different things. Conventional dimensioning and tolerancing sort of ties them together for convenience. Sometimes it doesn't tie them together, and that causes problems. So what is a dimension? A dimension is the number that does one of two things to a feature. It locates a feature or it defines the size of a feature. Now, what is a feature? I like to, in blueprint reading, I always start out with a six-sided box and say, how many features does this have? Well, it has 6 faces. It has, each face has 4 edges, 4 vertices. Each one of those is a separate feature, and at some point, sometimes you have to control each one of those independently. So even simple parts have a lot of features and may or may not require a lot of dimensions to define where those features are and how big those features are. Sometimes you don't have to do that, but very often you do. So a tapped hole, a slot, a groove, an edge, a surface, all of those are features on a part and require some level of definition, and the dimension is what does the definition. It is, or should be, the ideal number for that feature, so that if the engineer had his way, all he would get was parts that had those numbers exactly on the part. And every part would be exactly the same. And ideally, if he designed it correctly, that part would work the best it ever could. Okay, so now reality introduces itself and we realize that we can't make every dimension, even on simple parts, exactly the same. For one thing, it's not cost effective. Two, it's really not possible. When you start measuring at a certain level, you'll notice that if you measure finer and finer and finer, eventually you're going to sort of drift away from that perfect number, that dimension. And then you have to decide, is that difference between the perfect and the real enough to have an effect on my parts? And that's what the engineer does when he applies the tolerance. He says, yes, I would like that dimension to be exactly what I put down on the piece of paper, but no, it doesn't have to be. You can be larger or smaller, and by how much? And that's what a tolerance is. So we start out with this notion of less than perfect geometry. One thing that GD&T is going to do is bring us back to that concept of the dimension as a perfect thing, that we don't have to worry about the effect of tolerances on it. We just define what we really want. And then the tolerances applied separately. The first problem we encounter is, what is my tolerance? Do I deserve a tolerance? Do I get a tolerance? Well, yes, you always get a tolerance. Everything has a tolerance. Now the question is, how do I find out what that tolerance is? And the first problem a blueprint reader or an engineer runs into is, what is the tolerance on something? If I buy a bar of material from a material supplier, I have to try to figure out, it says it's 6 inches wide, but is it really? Before I get it, before I can actually measure it, hopefully I can go to some publication somewhere and figure out what it is. There's no drawing for it, but it could be slightly undersized, it could be slightly oversized, and will be. And some industries publish those standards, some don't. So immediately we run into a problem is, if I let you use a piece of raw material without machining it, how big or how small is it actually going to be? Is it going to have an effect on me? So I go looking for tolerances published somewhere. So tolerances can be published for routine commercial things. For something that's going to be made off of a drawing, the same thing sort of applies. Sometimes tolerances are not on the drawing where they really should be. They might be in a company publication. They might be in a standard somewhere. Who knows? Until they show up on the drawing, we really have to sort of scrounge around and look for our tolerance. In the best of all possible worlds, that tolerance would be very clear and explicit on the drawing. Sometimes it is, sometimes it isn't. But even when the tolerances do show up, they're going to be expressed in a number of different ways on the drawing. And this causes a lot of confusion and a challenge to the person trying to interpret it to say, what is my tolerance zone? How much running room do I have? So we have to sort of figure out sort of the standard ways of putting these tolerances on a drawing and learning how to deal with them and sort of make them at least look the same, so that the parts will behave the same. Okay, so we start out with the scenario where the dimension is applied with a tolerance. Unfortunately, it can be expressed a number of different ways. Okay, so let's look at those expressions of dimension and tolerance. Now obviously it's pretty clear that the dimension intended is 1 inch. The engineer has done a good job. He's given you a reasonable tolerance of plus or minus 10 thousandths on the first instance. So that expression, that way of expressing a nominal dimension or a perfect dimension of 1 inch and giving you a little bit of tolerance on either side, 10 thousandths plus, 10 thousandths minus, is a great way to express a dimension and tolerance. We can work with that pretty easily. But that form, and we'll give it a name, we'll call it the bilateral, since there's a little bit of tolerance on either side of the dimension. That is a bilateral expression of tolerance, or a bilateral form. If you look at the next one down there, we have the same nominal dimension. Here we have all the tolerance shifted to the plus side and none to the minus side. Just below that, all the tolerance is shifted to the minus side and to the plus side. Those two expressions are unilateral expressions of tolerance, where the designer, for one reason or the other, has not given you one side of the tolerance, and he shifted all the tolerance in one direction. We're going to see here very quickly that we can change that form, and without having any effect on the part. Our ability to manipulate that tolerance expression is it's a fairly simple exercise and often very useful. Often students ask me, why would an engineer do that? There are reasons why he would pick one form or the other, bilateral or unilateral. Sometimes it's a little bit easier when we're doing calculations to do them in one way or the other. Very often in certain design scenarios, you want to make sure that you don't get a thin or a reduced material. You want as much material as you can get for strength. So you make sure that all the tolerance heads in the plus direction. If on the other hand, you want to, on average, make the part as light as you can, like in an aerospace application, you would often throw the tolerance to the minus side so that the machinist is always working towards getting the least amount of material into the design. If you look at the last one over to the right there, we see that even the bilateral form can take sort of a weird form where the tolerance isn't equal on both sides of the dimension. In this case, 15 thousandths goes to the plus and 5 thousandths goes to the minus. All of these are valid ways of expressing a dimension and a tolerance, and they all have or they will all lend themselves to a way to make them regular, so that if you for any reason want to see these all in one form, you can convert them. Now it's just like any other number manipulation. You have to be careful. You have to make sure that you don't change the intent of what the engineer did when he put that dimension and tolerance down. Okay, but for right now, what I want you to remember is that dimensions can be bilateral equal, bilateral unequal. They can be unilateral plus, unilateral minus. And I'm going to go on the board here now and add one more form that you will see. This is sort of the best form, I think, for expressing tolerances, but when we do this, we sort of lose the sense of having a dimension at all. So I'm going to take the first equal bilateral dimension and tolerance there, 1 inch plus or minus 10, and I'm going to express it in a different way. I'm going to add the plus side of this to the dimension, and I'm going to subtract the minus side from the dimension. And what I've done here is I've converted the form of that equal bilateral expression into another expression, or another form, that I'm going to call the limit form. And I think it's pretty obvious why it's the limits. It's the largest and the smallest dimension that an acceptable part could have. Now, is that useful? Yes, it is, because if you're making parts, it's very clear to you that if you make a part that has a feature that's supposed to be 1 inch 10 thousandths, if it's 1 inch 11 thousandths, you've got a problem. You have to remove some material, or if it's a hole, you can't do anything, you have to scrap the part. So anyway, it's a very explicit expression of what numbers are important in terms of making that part and meeting the requirements of the design. What's lost here, though, is what is the dimension? You lose the dimension in this conversion from bilateral to unilateral, and in some instances that really isn't super important. But if you're a machinist, what do you interpret as the dimension there? What would you shoot for? If you said, oh, I've got plus or minus 10 thousandths, and I can make these parts to plus or minus 1 thousandth. You have to shoot for one of those numbers. Now, you know, sensibly, you probably aren't going to shoot for 1 inch 10 thousandths or 990 thousandths. You're going to give yourself a little running room, so you're going to head into that range. Pick a number and say, I'm going to set my machine to that, and hopefully the dimensions won't drift more than a couple thousandths in either direction, and I'm good to go. And you will be. But again, that sense of a perfect dimension that is the ideal location or size of a feature is now gone. Not a super big problem, but it's something to think about, and one of the things that GD&T is going to resolve for us. Okay, now the important thing here is, now that we see all of these forms, I want you to be comfortable with being able to convert from one to the other. And the way we start that process out in all instances is to convert whatever form we get, a unilateral in either direction, or equal or an unequal bilateral. We can convert all of those into a limit form. And when we do that, it's going to be kind of interesting, because all of a sudden you're going to see that dimension and that tolerance in a different way, and it will tell you something about that feature. So let me convert those, and we're going to see, as much as these dimensions look the same and the tolerances are sort of the same size, we're going to see that those are not equal to each other in any way. So let me do the conversion. Okay, so I've now converted with some very straightforward arithmetic each one of those different forms into the equivalent limit form. Now let's look at those limits. Are they the same? Well, no, clearly they're not. Each one of them has a different upper limit. Each one of them has a different lower limit. So as much as they look the same, they all start out with a 1-inch dimension, and they all have a total of 20 thousandths tolerance range. We can see that we're not going to have the same results. They're not going to work independently if we have or work together. There are going to be problems with one or all of those parts if we're expecting them to meet a consistent range of size. All right, so let me introduce a term here so that we can do these conversions easily. And one of the terms that I want you to remember, especially for the purposes of the test, is this difference. If we take the upper limit and subtract it from the lower limit, in each case, the difference between the upper limit and the lower limit is 20 thousandths. That difference between the upper limit and the lower limit is called the allowance. And we're going to use that allowance, one, to do these conversions and to check ourselves to make sure that we've converted correctly. And we're also going to use the allowance later on in GD&T to adjust the size of the tolerance zone. So that concept of an allowance, which is the total range of the tolerance, no matter how it's expressed there, each one of those has the same allowance. So keep that term in mind. Okay, now We won't spend too much time on this. I want you, this should be review from blueprint reading. We talked about this pretty significantly, and I will want you to be able to do these conversions from any one of these forms into the limit form. And obviously from the limit form you can convert back to another form. Let's do one of those anyway here. Let's convert this bilateral into a limit form, or into a unilateral form. If we do it in this sequence, if we do it from whatever form we start out with into limit form, we can now pretty easily express this as a unilateral, just by picking one of the limits and adding the allowance. Or could have picked the upper limit. Okay, so now in fairly short order I have this as the original given bilateral form. I've converted it into limit form, and I've converted it into two unilateral forms. We can do that all day long. The key to any conversion is always to make sure that the limits do not change. So when you do this, you'll always want to check yourself and make sure that if you do the arithmetic in the form that you ended up with, you'll still end up with the same limit. So let's go ahead and do that. 990 plus 20 thousandths is 1 inch 10, and 1 inch 10 less 20 is 990. So my limits are the same in both of those instances, so I've converted successfully from bilateral to limit to unilateral in one direction, unilateral in another direction. And again, you can practice this. It doesn't take a lot of practice, but the key to this and the key to all technical work is keeping your numbers straight. And part of that is to the extent possible, don't do the numbers in your head like I just did. It's easy to get crossed up, and that's why you always want to do this check. Okay, so that is tolerances as they are traditionally expressed on a drawing. Now again, you can only hope that if you don't have GD&T on your drawing, you'll see your dimensions with a tolerance attached to them in this fashion. Tolerances don't necessarily have to be stuck on the dimension. They can be expressed in a note. Very often, drawings in general will have a table down in usually in the lower left-hand corner called the default tolerance block. And it tells you that if you have a dimension that doesn't have a tolerance expressed, depending on how the tolerance or how the dimension is expressed, you get a certain amount of tolerance, and it'll list it. And it'll say if the dimension is expressed in 1 decimal place, you get plus or minus 50 thousandths. And if it's 2 decimal places, you get plus or minus 25 thousandths. And 3 decimal places might be plus or minus 5 thousandths. I am no big fan of default tolerances. They cause a lot of problems. They often are ignored or forgotten by the engineers, and they forget that the tolerances have to be looked at. You can't just make a default assumption. Now, back in the old days when we used to draw drawings and dimension by hand, we had to do that. We had to write every dimension and tolerance separately. Now the CAD systems put the dimensions on automatically, and you tell the CAD system to put all the dimensions and tolerances in 2 places or 3 places. So it's not unheard of to have a drawing with all three place dimensions where only a few instances would a plus or minus 5 tolerance even be necessary. So anyway, that's how I feel about default tolerances. I'd like to see them expressed, but the way they're expressed in this way can be problematic. And the very best thing you can do, I think, is to take whatever form you get and at least work out the limits. And that way you don't have any math to do in your head while you're trying to address that feature.